Yeah, so today I'm going to talk about drone remote sensing platforms and how they can be used to monitor changes in alpine environments. So these mountain environments are rapidly changing, and my work looks at how these glacial environments are transitioning to paraglacial environments. I'll talk a little bit about some of the obstacles to monitoring change in these environments, and then some of the solutions we've developed here in the Glacier Environmental Change Lab at Byrd, and then the development of UAS remote sensing platforms. So I was asked to give this talk to sort of summarize what we've been up to. I think people have heard a lot of grinding, like strange noises from cutting materials and putting them together in there, and like, what are you doing? So I guess this has been a long time coming. So we're going to sort of talk about some of the hardware we're putting together. So this will definitely be more of a hardware, materials, workflow talk than, I guess, underlying science questions, which I am very happy to talk with you about if you care to listen. This whole sort of, I guess, mission began with a trip out to Great Basin National Park in Nevada. And if this will work, I will show you where that's at. Hopefully you don't get dizzy. So Great Basin National Park is out there in the Great Basin region of Nevada, along the border of Utah. And it's a pretty dry environment where you've got these mountain systems that are sort of like islands that provide water and refuge for wildlife. They're pretty unique. And so they say this is the only mapped glacier in the in Nevada. So this is sort of an overview of the Great Basin area, but really what this is just showing is that this town out here is in a very dry area. So to clarify this a bit, you've got these mountains here, Wheeler Peak, about 13,000 feet. This is the town of Baker. And you've got a lot of these hydro resources originating in the park. And these dots here are an embedded sensor network that some researchers in geography have been operating for the last decade or so. Emily Sambuco has been looking at that. She could tell you more about that. But my interest has been in this little section here, this tiny little rock glacier under Wheeler Peak. And I guess we've been looking at some of the data related to these two sensors as well. So this is the study area here. And this is the rock glacier. It's pretty small, about 1/10 of a square kilometer. And it ranges in elevation from about 3,300 to 3,500 meters. And these features were formed largely with the accumulation of rockfall debris on these low-angle slopes at the base of now vanished glaciers. And that eventually is developed into this mantle of surface debris that insulates the ice and initiates the development of this feature, rock glacier. So in the past, previous field teams have used this innovative balloon system to look at it. And we got Jim DeGrand here from Geography Department. He built this stabilizer unit where they put a digital camera and they flew these balloons up over the glacier to capture as many photographs as they could of it. And as you can imagine, it was rather difficult to get these balloons up. Fortunately, I never had to do it, so I can't really say that. But it looks cumbersome. So our goal was to try to maybe simplify this a little bit. And the method that they used to sort of piece together these 3D models of the glacier to look at changes each year is very similar to the one that we used using our 2018 data. And that's this so-called structure from motion algorithm. And it's basically like kind of how our eyes work. We take in light from lots of different vantage points, and we sort of stitch that together. And the result is a cloud of tie points. And we can derive a digital elevation model looking at surface elevation from these point clouds. And we use differential GPS to correct the ground control points that we set. We tag in these photographs, and we been processing our 3D models at the Ohio Supercomputer Center, which makes things a lot easier for us. So this is an example of sort of what the mapping would look like using the balloon. So every one of these rods here is the angle at which these photographs were taken, and the blue kind of represents the coverage. So sort of a helter-skelter approach with the balloon. Not much control over like where the wind takes it, and where the wind takes the balloon also takes the researcher at the end of the rope. So it can be a little sketchy from what I've heard. And in the past, these were some of the orthomosaics that were developed. So you can see not necessarily total coverage in 2015. There was total coverage in 2016. So we're really excited to try to achieve total coverage as well in 2018 so that we can make a comparison to 2016. Given this mismatch, previous analysis that was conducted by John Morgan Manos focused on some of the better mapped parts of 2015 and a comparison between the two of some of the lower lobes of this rock glacier. So these are the elevation models that were derived, and these are some of the surface elevation changes that John Morgan was able to put together. And here you can see this area sort of highlighted as the area of best annual coverage. And in this case, the green represents gains and the darker shades represent losses. And so you can sort of see some evidence of not only motion, but some of the underlying processes involved. And what John Morgan was able to, his best estimate for change over the 1 year between 2015 and 2016 for this area was about 5,200 cubic meters of surface elevation, or of volume loss. So our goal was to sort of enhance the stability of the system, to improve resolution and coverage, also improve safety by minimizing our need to be tied to a massive balloon that can drag you across a very jagged surface, and make fewer balloon hikes. So we did a lot of testing here in Columbus beforehand to sort of establish the workflow. We started out just kind of taking pictures helter-skelter all over some of these mounds. We used these 30 centimeter by 30 centimeter ground control points. And eventually we decided to become more systematic with things. So that made it a lot easier for us to calculate what our flight time was going to look like, what the velocity and altitude needed to be in order to achieve the ground sampling distance that we were looking for. This is an example of one of the early plans for surveying the rock glacier, where each of these black points in the center is a place where it would stop, take a photograph. Red lines are the flight paths, and then the blue squares are the overlapping coverage. And we tried to achieve 80% vertical and horizontal overlap. Originally, we thought, okay, we'll just set it at an altitude and it will work out. But we realized that if we did that, it would eventually have just flown right into the rock face. So we came up with a pretty interesting algorithm to follow the contours of the Earth based upon previous year's coverage, and some places we had to sort of make some calculations and watch what happened and really hope that we didn't hit the rock wall. And I'll come back to that because we've made some significant updates to sort of hopefully avoid those situations and going forward. A lot of these details may not be super interesting to everybody, but we flew at 230 feet and 550 feet above ground level, took a lot of photographs, took a lot of ground control points, and yeah, happy to return to this if anybody has any questions afterwards. So in 2018, we were able to also repeat total coverage, and there was no snow at this time of year, which made things a little interesting. Talk about that a little bit more in the future. Again, not sure this is super interesting. Some of these slides are from GSA, but in any case, more photos, more tie points, and we're working on reducing the total RMSE air for the XYZ. This is our 550 above ground level The 230 is an improvement in resolution, and we're working on merging both of those together to drop the air even lower. An example of what this looks like. Enough to pick out quite a few features. So, something we're going to be doing next is looking at do some like surface velocity fields by feature tracking. Again, 2 centimeters, and we're able to find Brian and John Morgan out there on the rock glacier collecting accuracy points. So what this means is that we're able to, as I said, use the structure from motion algorithms and the Ohio supercomputer's resources to stitch together these surfaces, form meshes, and eventually overlay the orthomosaic. And we do that by tying it to those ground control points that we use. Evaluate the model using the accuracy points. And we can derive hillshades like this. So they give us a really solid look at what sort of features we're looking at. So in this case, for the Lehman Rock Glacier, it's interesting that there are some of these distinct features. You see 3 sort of distinct lobes here. One up here, another one here, and another one down here, which I would say probably suggests instability in the Cirque Glacier that was there previously. If that glacier had remained stable throughout the late Pleistocene and Neoglacial, then the upper and middle lobes would probably not have developed. Glacier retreat probably provided room for each of these lobes to develop. And something else that's interesting to note I didn't talk about was to scale about right here down below the glacier is a 5,000-year-old bristlecone pine grove. So that sort of constrains the maximum age, and it's likely that these guys, they couldn't be that old, right? So 1,200 years before present for some of the lobe development seems about right. Resolution. So because we got full coverage, we were able to look at the changes between 2016 and 2018. Both of these images show the same sort of thing. It's just different color scales. And what this has yielded thus far is about a 49.5 or 46,000 cubic meter volume loss. The next step to really look at this was to remove or mask out some of the snow features. So I guess this is sort of looking at it again here, and you see that the outliers that we see are related to the presence of snow between the different years. So we wanted to take that out so it wasn't biasing the sort of color ramp that you're looking at here. And that's what this is. So now this has been corrected to remove the snow, and we've got a more normalized scale here. So red would be a loss of 2.5 and goes down to a gain of 2.5. And you see that the upper lobe here is behaving differently than this one. So looking at that a bit closer, these are the ground control points that were used in 2016 across the glacier, and these are the ones that were used in 2018. And collectively, those are all the ground control points that we used to create this map. Each of those were recorded for 5 minutes at the ground control point. So something that we're looking at in relation to this now is because it was clear skies throughout that time, we're able to infer or estimate what the solar radiation looked like at the time, and we can create a far better resolution of what exactly that looks like and try to account for what could lead to surface elevation changes like this. So Emily's looking at climate patterns, microclimate patterns in the area, also looking at radiation, and going to figure out what this might mean for the hydro resources below. So I said that this was a lot to do with hardware development and sort of the capabilities here. So it's quite the shift, but a necessary one. Switch to Peru here. So in the Cordillera Blanca of Peru, which is about where this star is here, you've got a heavily glaciated mountain range where you find about 70% of the world's tropical ice. And these are critical water resources. And because it's so important to the folks living in these seasonally dry valleys below along the Rio Santa, they often live in close proximity to these glaciers, water resources. So what's interesting about this, and this is where a lot of my interests lie, is that what we're seeing is sort of a destabilization of the tropical cryosphere. And this is manifest in many different ways. We've got the rising of the 0-degree isotherm, which has been documented by Brian and Lonnie here. Acceleration of the disappearance of these tropical glaciers, intensification of hydroclimatic events, and this is likely going to lead to a rise in geohazard frequency and magnitude, a decline in water quality and quantity, and I would argue a need for anticipatory risk management. And the best way to sort of address that, I think, is to overcome the dearth of observational data that exists, which is a problem endemic to really anywhere with a complex topography. So just some context. I think a lot of folks in this room have heard me talk about this in various ways or are familiar with the area, so I'm going to just keep moving along. But this is Huascarán here, and there was an event in 1970 where this mass movement was triggered that resulted in the town of Yungay being pretty much wiped off the map. This is something that happens, I guess, in this region more often than not, I guess, in many other places. It's a very seismically active region. And so the thing to note here, I mentioned that there are a number of heavily populated, densely populated areas situated below some of these glaciers and these lakes as well. A lot of my interest involves the effect of glacier retreat on slope stability in the region. As the glaciers retreat, there's a loss of cryostatic pressure, can lead to destabilizing the ice. But there's also this risk of ice avalanches or landslides hitting the waterways, which can then trigger mass movement down these narrow valleys into the populated areas. So some areas that have been identified as being potentially hazardous that we're hoping to look at this summer are some of these outcrops, overhangs. There are many ways to model this. The RAMS modeling environment developed at ETH in Zurich is perhaps the most widely used in the Alpine hazards community right now. Unfortunately, especially for this region, a lot of the models are developed using qualitative assessments of what might happen. There isn't much volumetric data out there as to what these ice crops really look like. And the resolution of the digital elevation models that they use also sort of dictates the flow. In this area, the only sort of continuous or contiguous data that you can get would be ASTER or SRTM, both which are available at 90-meter resolution. So here's an example of what something like this might look like downriver, where you've got the flow height estimate, and you can see that even into town, you've got flow heights reaching 15 meters based upon some of these slide events. And I mentioned the importance of well-constrained surface elevation data. Something that is important to note here, as we're going to be looking at this, is this Lidar data that was collected in 2008 by Brian Mark's research group. Oliver Wigmore also collected some data, the blue sections. Yellow is some of the sites that we're hoping to target this summer. This area in particular is of interest. We've got Lake Palcacocha here, and then Tokiarahu here, and this area in particular has been studied quite a bit. Again, many of you are familiar with this region. This is Palcacocha, and there are a number of sites that have been identified, or features that have been identified as potentially unstable. And what can happen as a result is this glacial outburst flood. So when mass enters the water body, wave is propagated, breaches the dam, and this can lead to mass movement down valley. There's many mechanisms that can result in this. Additionally, these dams might be ice cored, so they might their surface might depress over time. That's also a risk. And a couple weeks ago, this was captured above Lake Palcacocha. So you'll see right up here, small slide, large wave propagation. It doesn't take much. I'm going to try to bring that back. So it's really impressive to me how such a small bit of mass entering the water body can lead to waves like that. For reference, this is about, say, just under a mile long. So this has led to the origins of the mountain drone team. And that's what I was asked to talk about. So here we are. The goals of the mountain drone team were to basically create an autonomous remote sensing platform that would be our eye in the sky in high altitude environments, to observe changes, to collect data similar to what we saw in the beginning of this presentation, but also have a heavy enough payload capacity that we could outfit the platform with other instrumentation as well. So what we've worked towards is not only something fully autonomous, but also a zero emission vehicle and workflow. So something that we can charge with solar panels in the field, something that's capable of high altitude flight. Ideally, we've been shooting for 6,000 meters above sea level. Something that can carry, ideally, up to 5 kilograms, and something that enhances our spatial, temporal, and spectral resolutions that we're working with. So there's a really distinct dry and wet season in this region, and for many months of the year, it's very difficult to see what's going on due to cloud cover. Shadows also obscure topography quite a bit, so we wanted to basically create a tool that we could use to see something on demand and at a closer vantage point. And then depending upon the instrumentation involved, see it in different ways along that electromagnetic spectrum. And build off what we've learned from the structure for motion algorithms by incorporating active sensors like Lidar. And consequently, not only get up and see some things that have been difficult to observe, but reduce human exposure to hazardous field conditions as part of that. So my goal was to bring together a team of students capable of such a crazy undertaking, and a lot of them are here today, but we've got Nishay here somewhere. He's the chief pilot. He's got the most skills of all of us. Evan's been taking point on putting together the flight controls and the autonomous system. Jake isn't here, but he's a whiz on the 3D printer. Joe's been helping out with developing the autonomous system. Cole also isn't here, but he's been heading up the calculations on whether or not we'll be able to fly at these altitudes. Gus has been helping integrate sensors and has been doing a stellar job. Michael isn't here, but he has been learning how to talk to the Ranger, which is what we call her, and that can sometimes be very difficult. But I'm super proud to have brought together such an awesome team from all across campus. It's a big campus, and we've got a lot of resources here. Sometimes it's hard to get connected with them, but we found each other. And yeah, here's everybody. Great team. We started out with, honestly, just a concept design that we didn't quite know what to do with. And that's evolved into, I think, something far greater, perhaps more audacious as well. We spent a lot of time over the last, better part of the last year developing this thing, working in the lab. This is where the strange sounds have been coming from. We've got a test drone that we use outside. If we program a flight, we'll always run it on, this is probably a better image of it. If we program a flight, we always run it on this guy first, just in case it decides to fly into a tree or the pond. There are 2 ponds out there. They're hazardous. So it's been great. And, some of the things that we're going to be able to do with this are use these active sensors to map out these environments to a scale that we really couldn't achieve with just structure for motion. And it's not like we can go out and lay ground control points over crevasses, right? So being able to use active sensors has been a real solid development in this. One of the goals has been to constrain surface elevation. That was definitely the goal right off the bat. And that's sort of evolving. This is a bunch of text, but the main thing here is that with this system, we'll be able to learn quite a bit about slope stability, be able to constrain topography and slope geometry. We'll get a better idea of where mass movements have occurred in the past, and better understand the catchment characteristics, extreme order, where water is flowing, how that might be changing, and then a better idea of these dam characteristics, whether or not they're ice cored or not. And these are all factors that directly influence the conditioning or triggering of these glacier-related hazards in alpine environments. There are also cryospheric factors as well, like the thermal properties of the glacier, glacier hydrology, crevasse detection, and this sort of gets at, I guess what excites me about this is the evolving science questions and the evolving instrumentation that goes along with that. I'm excited to say that we'll be able to show you some of the Lidar mapping capabilities here in a moment. We've got a new non-repetitive scanning Lidar, which is very different than a lot of the Lidars that you might have seen previously. So we're super excited about that thing's capability. It's 600,000 laser points per second. It's got 100 degree field of view. That's this guy here. We're also working on incorporating a net radiometer, which will allow us to constrain radiative flux in a spatially distributed manner across these glaciers. There's an infrared radiometer for measuring the surface temperatures. I didn't really mention this, but there is a laser altimeter on the drone that allows us to maintain constant elevations. And when we're flying in places where we don't know the surface elevation, that allows us to overcome the challenges we face in Great Basin. We've got ultrasonic sensors that we sometimes position on the ends of each of these arms that allow us to know when we're approaching something, and it'll back us off. We've got a sonic anemometer that we're working on, which is part of like a total weather station that measures 360-degree wind speed and direction. It can also provide sonic temperatures, and that's like the radiometers. That's at 10 hertz, and probably missing some other things as well. But honestly, what's exciting about this is we started out thinking, okay, let's measure surface elevation changes, and maybe then we can get a rough estimate of volume loss. But that's now evolved into like what is possible if it can carry this much weight, and that's moved beyond surface mass flux changes into surface energy flux questions as well. So some of the things we'll be looking at are with, say, the weather station would be we can assess a vertical column for water vapor changes. One of the neat things about having an autonomous system is what's happening or we can get a better idea of what's happening at night without endangering field crews. There are a lot of potential applications here, and now that we have come a long way in building this thing and have confidence in its abilities, we are more free to pursue those going forward. So that was a lot to cover. Hopefully you stuck with me there. And so I just want to say thank you to everyone for your attention, and thank you to the folks who helped make this happen. We've had a lot of support, and we couldn't have done it without, obviously, the Byrd Polar Climate Research Center community, the Sharp Innovation Commons, the Ohio Supercomputer Center, the School of Earth Sciences, and the Innovation Studio. So with that, I think I can field some questions, and we were going to demonstrate ways in which we can